Assalamualaikum and a very good morning. My name is Manoroda, and in this presentation, I want to talk about chronic kidney disease prediction. So this project aims to develop a deployable CKD prediction application using machine learning to enable early identification of chronic kidney disease by implementing Streamlit-based web app for real-time patient data input and prediction. So the problem that we are facing are the current diagnostic methods rely heavily on periodic laboratory tests, which can be invasive and often detect the disease at late stages. So the objectives of this project is to collect and process the UCSCKD dataset and then perform the exploratory data analysis. With the information, we can develop a machine learning classification model. And after that, we can evaluate the model created by using accuracy, AUC, R-squared, MSE, and techniques like K-fold cross-validation. There are a few steps in constructing the model. We have 4 phases. The first phase is data preparation, where we clean the data by handle the missing values and duplication. After that, we can transform the data by normalization and label encoding, and then we can feature select. And for phase 2, exploratory data analysis, we do a statistical summary and data visualization using ANOVA and heat maps to determine future relationships. And after that, we can do model development and training. We split into training and testing. For training, we use regression analysis, which are simple linear and polynomial regression. And after that, we test the model by using implementation of random forest, GNB, and logistic regression. For phase 4, which is evaluation optimization, basically we do additional steps to prevent overfitting and underfitting, like AUC, MSE, and R-squared, and K-fold cross-validation. The dataset that we used via Kaggle is the UCI machine learning repository, where they have 24 different attributes with 400 instances, as we can see over here. There are 4 different categories of these attributes. The first one is demographics, for example, age. And for vitals, like blood pressure, urinalysis, albumin, and sugar. And for blood chemistry, the creatinine, hemoglobin. And for medical history, hypertension or diabetes. So the first type of data cleaning, we basically remove ID column and the 4 sub-attribute into numeric type. And then after that, we can handle missing values. The missing values are filled using mean of the respective column. And for categorical value, we fill the missing values with mode. And for data normalization, we use a mean max normalization to skill select between 0 and 1. And for data meaning, for example, age, we separated into 3 different categories: young adult, middle age, and senior. And there are indicator variables as well, where the target variable CKD equals to 1 and not CKD equals to 0. And several other feature encoding as well, which are one hot encoding, which is HDN yes, hypertension yes, or DM no, or DM yes, and several other things. And after we have cleaned the data, we do exploratory data analysis. So the first is descriptive statistic. We calculated the mean, standard deviation, and variance for these categories, which is age, BP, VGR, BU, and all that. And after that, we can do a grouping analysis, where we group the dataset by the target variable classification: 0, not CKD, and 1, CKD, chronic kidney disease. And we can see which mean is high or low in the CKD or non-CKD group. For example, hemoglobin over here, we can see that hemoglobin levels which are high have more mean in 0, which are not CKD. So if you have high hemoglobin level, you don't have CKD. And for ANOVA, we basically use ANOVA to analyze the variance. We use one-way ANOVA to test if the difference between 2 hemoglobin levels is significant to predict CKD. And as we can see, p-value is very low, therefore very significant as predicted for hemoglobin. And after that, we do correlation analysis. As we can see in the heat map, we have top 15 features that have the highest correlation. They are separated into 2 different correlation. The first is positive correlation, and the second is negative correlation. As we can see, for negative correlation, the low hemoglobin level it is, the higher chance of you getting CKD. And as we can see, for albumin, AL, the higher the albumin level in your urine, the higher chance of you having CKD. So I pass the stage to my friend Angshumi to explain the model development.
So for the phase 3 and the phase 4, it will be the model development. So we tested 3 algorithms which using the logistic regression, the various, and the random forest. So for our evaluation, it shows that our random forest was the superior model, as it does achieve an accuracy of approximately 99% and has a perfect AUC score of 1.00. We verified this robustness by using the tenfold cross-validation. It obtained a mean score of 0.99. This These results show that and prove our model is generalized and not overfitting. Our features importance analysis also reveal that hemoglobin specific gravity and the serum creatinine are the most critical indicators for the disease. So next I'll pass to the Haziq for the data you said.
Hi, my name is Muhammad Haziq. Moving on to our results, we evaluated three different machine learning models to find the best one for our application: logistic regression, Gaussian knife bayes, and random forest. As you can see in the table, random forest outperforms the others significantly. It achieved an accuracy of approximately 100% compared to 96% for logistic regression and also 95% for knife bayes. To confirm these results, not just a fluke, we look deeper. The confusion matrix on the left shows our random forest model made zero mistakes. It corrects identified all healthy patients and all CKD patients in the test set. On the right, the ROC curve shows a perfect AUC score of 1%, of 1. This confirms that random forest is the most reliable model for this critical medical task. So we selected it for our final application. Now moving on to the app demonstration, I'm going to demonstrate the actual application that we built using Streamlit. Here on the left sidebar, you can see that we have the patient data input. We organize the 24 input into logical medical groups like demographs, blood chemistry, and urinalysis to make it easy for doctors to use. So I'm going to input a scenario where it's a healthy patient. Let's test a healthy patient profile. Someone with normal blood pressure and high hemoglobin. I'll click analyze and inspect. The result will show that no CKD is detected, indicated by the green color. Here you can also see that how the model finds the result and predicts the prediction. And also, you can see here, if we change the input, thus the prediction, if the patient has CKD, the diagnosis result will indicate the color red. So, also, below the result, we have our explainable AI section. This chart shows why the AI made the decision. In this case, the low hemoglobin was the biggest factor, and this density plots compared the specific patient to the general population, showing exactly where they fall in the danger zone. So, that concludes our presentation, and we successfully deployed a highly accurate diagnostic tool that bridges the gap between raw data and actionable clinical insights. Thank you.